Okay, this video is for AP Calculus, and we're going to talk about integration by substitution, which is the most common method that we need to do for integration, other than just using what we're calling the integration shortcuts, just the memorized rules for integrating families of functions. Integration by substitution is the integral version of the chain rule for derivatives. So just to kind of remind ourselves of how chain rule works, if you have a function here, which is a composition of functions. So you have a function that's inside another function. So here we have an outside function that is something to the fourth power, but inside that there's another function, x squared plus 5. Anything other than just x, well, that means that you can instead replace that. You can label this inside function c with a letter, like let's say u, and then take the derivative of that. That would be called du dx, and in this case it would be 2x because the function is x squared plus 5. And then you can rewrite this y function using that symbol u. This is now y is u to the fourth, so you can take the outer derivative, which would be labeled dy du, and that is 4 times u cubed. And then the chain rule says that if you want to find dy dx, then that's going to be dy du times du dx, because the du's would cancel out. Right? The dy du part is the outside derivative, and so the outside derivative here is this 4u cubed, but we just replace u with x squared plus 5, so that's just taking the outer derivative, 4 times the inner cubed, and just leaving the u unchanged. But then this is the reason why we have to multiply by the derivative of the inside function, which in this case is 2x. So this is useful and required whenever you have a function inside of another function. Okay, so integration by substitution is the integration version of this. If we have an integrand where a function is contained inside of another function like this, what we'll do is explicitly write the symbol u, which is why this is called u substitution often. And then we'll write out, we'll set this inside function equal to u. And then we're working on what I just like to loosely call the toolkit. It's just some work that we're going to have on the side that allows us to have some tools to substitute into the integral itself. So if we're defining u to be this inside function of u is x squared plus 5, then I can take a derivative of u and get du dx. Now in this case that would be 2x. And then I can multiply both sides by this differential dx. So that means du is equal to 2 times x times dx. And then I can substitute things from here into this toolkit, or into this original integral. So if I substitute into this integral, I have the integral of 4, and I'm just going to bring that 4 outside. But this structure can be rewritten as u cubed, so that's u cubed. And this whole 2x dx is this, which means we can substitute du for that. So the purpose of u substitution is to change the letter of integration, the variable of integration. In the original integral, the variable of integration is x, but after we do a u substitution, everything in the integral is now this new letter u. And the idea is that this should be simple enough, but then we can just use our integral or antiderivative shortcuts to do the integration. So the antiderivative of u cubed is 1/4 u to the fourth. We still have a 4 here, so that would cancel. That's u to the fourth plus the integration constant c. And then finally, from our toolkit, we substitute x squared plus 5 in for the u, and we get the result. So it's the quantity x squared plus 5 to the fourth power plus c. And that's how u substitution works. There's 4 steps to it. First, we're going to define the inside function to be a letter u, as typically used. We're going to find the derivative of u and solve that for du, right, which is going to allow us to group possibly some things with this dx, but to substitute out the dx. We're substituting from the toolkit into the original integral to obtain a new integral using this new variable u as the variable of integration. And then we integrate using our shortcuts, and finally resubstitute u at the end. Okay, so we're just going to see a bunch of examples of this. You can try pausing the video and then unpause to see if things are matching up. So for this first one, number 1 here, I would identify this inside function. It's clearly inside of the square root. So I'm going to define that as u. U is 2x cubed minus 3. And then because I'm going to eventually have to substitute out that dx, I'm going to take the derivative here, because taking the derivative will give me du dx. And in this case, it is 6x squared. And then if I multiply both sides by dx, I get du is equal to 6x squared dx. Then I'm going to rearrange this a little bit. So first of all, I'm going to take this part here and write that as u to a power, but the square root is the same as 1/2 power. And then I have this x squared dx left over, right? So in my toolkit, I have an x squared dx here. To get that by itself, I'm going to divide both sides by 6 over here in the toolkit. 1/6 du is equal to x squared dx, which means I can now replace this x squared dx with 1/6 du. Right, now at this point, everything has been changed from the letter x to the letter u. And so I should be able to hopefully integrate this just using integral shortcuts. So I'll take the 1/6 outside, and then we'll do the integral. So now we can use the power rule here. This is 1/6 still. We're going to add 1, so 1/2 plus 1 is 1.5, or 3/2, divided by 3/2, plus our integration constant, which I can write as 1/6 times 2/3. And then this u, I'm going to resubstitute that as 2x cubed minus 3 to the 3/2 plus c, and we're done. If we want, we can simplify this a little bit, the constant, but this is the structure that produces the answer. Okay, so if you tried that on your own, hopefully you got that right. We're just going to do a couple more examples before we look at some more complicated scenarios. Go ahead and pause the video and try this next one as well. What's the inside function make that u to start with? All right, so the u in this case would be 1 minus x to the 4th, which means when we take our derivative du dx, that's going to be 0, and this is going to be negative 4x cubed. When we multiply by dx, we get du is equal to negative 4x cubed dx. And now I start substituting. So first of all, this part here can be replaced with u to the 5th power. And then this x cubed dx, I've got that here, so I'm going to divide by a negative 4 and get negative 1/4 du is equal to that x cubed dx, which means I can substitute those things. Everything here is multiplied, so it can be rearranged as needed, with negative 1/4 times du. The negative 1/4 will bring outside. And now I've just got a simpler integral that I can use shortcuts for. So I have my constant outside. The antiderivative of u to the 5th is u to the 6th divided by 6 plus the constant c. And then we'll finally replete this. I'm going to multiply the 4 and the 6 together to write this as negative 1 over 24. U is 1 minus x to the 4th, and that's to the 6th power plus a c, and that's the answer. All right, so once you can identify the function to make a u, if it's clearly a function visibly inside of another function, it's easy to see that. We're just going to try a couple more here. Now, let's try something here. Sometimes the selection for u isn't as obvious. It looks to me like 1 minus x here is the function, the u that's inside. So I'm going to try this, but I'm going to do this in red because I actually know ahead of time this is not going to work. But let's say that I did decide to make u 1 minus x because that's inside this function. So the derivative here, the derivative would be, let's see, negative 1. So du would be negative times dx. And that means that this dx is negative du. So now if I try to substitute, what I'm going to get is an integral of, let's see, this is 1 over the square root of u. Then I've got an x squared dx left over. The dx can be, well, this would work actually, but it's going to be trickier. So we can try for the dx replacing this with negative du. But what will we do about this x squared that's left over? Well, in this part of the toolkit, we could solve this for x, right? If I brought x to this side, it would mean that that is 1 minus u. And that means that we can replace this x squared with 1 minus u squared. But unfortunately, that is not making things much simpler. Although I think we could continue. In fact, let me show you how we could continue here. We could multiply this out, and that would be, I'm going to actually raise this up to the top here and make this u to the negative 1/2 power. And then I'm going to do FOIL here. That's the same as 1 minus 2u plus u squared. I'm going to bring the negative outside, and now everything is in terms of du. And then finally, I'm going to distribute this to all of those. It's pretty complicated, but we could make this work. That's going to be u to the negative 1/2 minus, and now this is a 2 times a u times a u to the negative 1/2, which is a u, so it's 2u to the 1 minus 1/2 is positive 1/2. And then if I multiply these together, I have a u to the negative 1/2 and a u squared. And so 2 minus 1/2 is 3/2. Right, so we could actually do this and then do separate integrals for each of these. Let's go ahead and do that. We have a negative here. So what is the antiderivative of this? That is u to the positive 1/2 divided by 1/2. We have a minus 2. This is u to the, let's see, 3/2 divided by 3/2. And then we have plus u to the, if we add 1 to 3/2, 5/2 over 5/2 plus a c. And then we can replace each of those u's with 1 minus x's. So this would be a negative. Let me distribute this now. And this is 2. 1 over 1/2 is 2. 1 minus x to the 1/2 power. Let's see, this would be minus minus, so that is plus. And then we have a 2 times it. Divided by 3/2 is times 2. Divided by 3, yeah, 3/2 is times 2/3, so that would be 4/3. And then 1 minus x to the 3/2. And then we have a negative 2/5, 1 minus x to the 5/2 plus c. Right, so if we did use the inside function here as 1 minus x, that's actually the right choice. So yeah, I'm not sure why I did that in red. This is actually the correct way to do the problem. And it's pretty tricky, but the key point in this example is that if you have the leftover x's after you've done your substitution, you can take your original line that defined u and solve it for x, and then use that to substitute. Frequently what will happen is you'll end up having to distribute something so that this breaks into multiple simpler integrals. But in fact, this is the right way to do that problem. Okay. Now this next one is, let's see, yeah, maybe a little more simple. Figure out what the right substitution is for number 4. Pause the video and give that a try. All right, so the right substitution here is going to be this inside function, which is 1 plus 1 over x. And let me also write that as 1 plus x to the negative 1, because I'm going to have to take the derivative to complete this toolkit. The derivative of 1 is, that's a constant, so that's 0. And this is going to be negative x to the negative 2, which is equivalent to negative 1 over x squared. So that means that du is equal to negative 1 over x squared times dx. And that's good, because I see I have a 1 over x squared here that I need to become part of the du. So rewriting this, I'm going to start with this part here. That is equivalent to u to the 1/2 power. Now we've got this 1 over x squared times dx, which is this. So that's equivalent to negative du. So just negative du to replace the rest of it. Bring the negative outside. And then do the antiderivative. So that is u to the 3/2 divided by 3/2 plus 2, which is the same as 2/3. And for the u, we will resubstitute 1 plus 1 over x to the 3/2 power plus c. So this is the final answer here. Okay. What about something like this? Well, let's try a couple things. I think in this case, I see that this structure here is equivalent to saying cosine of x, and then that is squared, which makes this cosine the inside function. So let's try that. Let's make that the u, cosine of x. The derivative of cosine is negative sine So that means du is negative sine x dx. And that means if I want to substitute this, this is going to be, let's see, first of all, if I bring this sine x down on the side here, actually let me rewrite this a little bit. This is equivalent to 1 over 1 plus cosine of x squared. I'll bring the sign down here so I can see that that's like that. And then that means that this is equivalent to 1 over 1 plus u squared. And then the sine x dx is negative du. So if I bring the negative outside, it's 1 over 1 plus u squared du. Remember we said that the derivative of arctangent is 1 over 1 plus x squared? That means that the antiderivative of 1 over 1 plus x squared is the arctangent of u plus the c. But the u in this case is cosine, so this would be negative arctangent of the cosine of x plus c, to go back to the original variable. So again, that inside function, it's harder to see here, but the cosine is inside of a square function here, so that's the appropriate choice. And one last one to try here for the main idea. The u here is going to be the 1 plus secant, because that's inside the square root function. So if I decide to make that u, I'll write this over here in the toolkit. The derivative is constant is 0, but the derivative of secant is secant times tangent, which means that du is equal to secant times tangent times dx. And that means this part can be rewritten as the square root of u, which is u to the 1/2. Then we have a secant tangent times dx. So all the rest of this together is just du. And that means the antiderivative is add 1 and you get 3/2 divided by 3/2 plus c, which is equivalent to 1 over 3/2 is 2/3. The u is 1 plus secant of x, for the 3/2 power, plus a c, and then we're done. Okay. So that's the mechanics, and typically you want to write this little toolkit over here on the side. Okay, one thing I want you to notice about why this is working is before I start a problem like this, where I can identify the u as the inside function. So let's just say that we're starting this problem over again. And I'm just looking at the inside function, and that's 2x cubed minus 3. Before I write anything, I'm going to just think in my mind, what would the derivative of that be? That would be 6x squared. And the variable part of that, the x squared, also appears in the integral, which means it's going to be what we need to build the du. Right? So whatever you have as the inside function, the derivative of that, at least the variable part of it, has to appear somewhere else in the integrand. Is that true here as well? We have 1 minus x to the 4th. The derivative of that would be negative 4x cubed, and there's the x cubed. That's why u substitution is going to work. The reason this is important to try to think about when this will work is that by the time we're at the end of this unit, we're going to have about 6 or 7 different ways to integrate. So this is just one of many techniques, and we need to learn when we can apply this technique. Right, here's another one. Now this is not as easy to see. 1 minus x is the inside function. The derivative is just negative 1. But what we have left over is simply an x, and we always have a toolkit that involves x, so we'll always be able to solve it for x in some way. But this is less easy to see. 1 plus 1 over x. You'd have to, I personally can't look at that 1 over x and just immediately see that the derivative is negative 1 over x squared. So I think I would just go on faith and say, okay, that's the inside function. Let's try it and see what happens. But here, right, this one, which is cosine, the derivative of cosine is negative sine, and there's the sine that we need. And then this inside function here, the derivative of the secant is secant tangent, and there's the secant tangent that we need to make the du. So u substitutions will work when the inside function's derivative appears somewhere else multiplied inside that integrand. Okay. So because that's true, some people call this whole procedure kind of the reverse chain rule, because we're sort of undoing that derivative on the inside, right? There's always going to be the inside function, and the derivative of the inside function is going to be somewhere else in the integrand. we can actually take advantage of that and do less writing. So what I've been showing where we are writing the toolkit is the formal way to show you substitution, and that's always allowed. You can definitely always do that. There are some situations when you might not have to write as much, and you can kind of just think about the fact that there's an inside and an outside derivative all present in the integrand. So let me show you how that would work. Let's take this problem number 7 and do it the traditional way for u substitution. We would identify the inside function here as 3x minus 2. We would take the derivative du dx, which is 3 in this case, and then multiply it out, and then explicitly show that this is u to the 5th, and then say, oh, that 3 dx is the du. So that gets absorbed into the du. And then we would complete the integrands, or the integral. So that's 1/6 u to the 6 plus c, and therefore 1/6 3x minus 2 to the 6 plus c. Okay, the other way to think of it is to just say, what is the inside function? I'm just thinking about this. The inside function is going to be 3x minus 2. So the derivative of that, right, the derivative is just 3. And that means that I have to have a 3 to go along with the dx to get absorbed, right? So what you can do is just kind of think this, or maybe write it. You can kind of think this. What's the derivative of that? That's 3. And just think, okay, that 3 there, along with this, is going to get absorbed, making the du. And so without writing the u explicitly, you can just say, okay, let's switch to just thinking about the outer function. So what is the antiderivative of the outer function? It is that to the 6th over 6, and this 3x minus 2 stays in there. And that inside, that derivative of the inside, the chain rule part, got absorbed, and then we just tack on the c. The same thing we got over here, but with less writing. So if you can see that right away, you're welcome to do that. And there are some circumstances that come up later where we have like multiple stages of integration, and the u substitution is just a part of a larger procedure where we might do that. We might not always write out the u. But if you feel like, okay, I'm not really totally seeing that, and you just want to go this way all the time, you're welcome to always do the u substitution and write it out. That's kind of the preferred way on the AP test anyway. Here's another few examples of that. So the formal u substitution over here on number 9 would be, we would identify the u and write u is 4 minus x cubed, right? And then we would say, all right, we've got, let's see, the derivative du dx is negative 3x squared, so du is negative 3x squared dx. And then I would rewrite this and say, all right, this is the same as 1 over the square root of u. And then I've got this x squared dx, which is the same as negative 1/3 du. And then I'm thinking, okay, that's the same as u to the negative 1/2. I can bring the negative 1/3 outside, and now I can do the antiderivative. So negative 1/3 constant, add 1 to the negative 1/2 to get positive 1/2, and divide by that. Add the c. Dividing by 1/2 is multiplying by 2, so that's negative 2/3. The u is 4 minus x cubed plus c. This is to the 1/2. All right, so this is the result here. Okay. Now, how do you do that without explicitly writing all of this? Well, you can just think in your mind, we've got an inside function. Actually, I would do one thing first, okay? If I'm going to do this, I'm going to try to rearrange this a little bit before I even start. So maybe I would say this is equivalent to having 4 minus x cubed to the negative 1/2. And then I'm moving this down. This is x squared dx. So you can kind of see how this is sort of an outside function, and the derivative of this appears over here, right? Now, what is the derivative of this inside function? Let's just note that. The outside function is this, right? That's what we're going to end up taking the antiderivative of. The inside function is this 4 minus x cubed. So what is the derivative of 4 minus x cubed? That's negative 3x squared. There's the x squared part. But for this to be absorbed, I have to have this be negative 3x squared. So I'm going to have a negative 3 in here. But if I decide to put a negative 3 in here, I have to balance it by, if I'm multiplying by a negative 3, I have to divide by a negative 3 as well. I'm just going to put that outside. So then what I'm doing is saying, all right, now that I have the derivative of the inside over here. I just have to undo the outside derivative. So it's that same thing, 4 minus x cubed, but I would add 1 to get 1/2 here, divide by that 1/2, and multiply by this constant. And that means I've got negative 2/3, 4 minus x cubed to the 1/2 plus c. So if you see that idea and you feel comfortable with it, you're welcome to use that in place of the traditional u substitution. Personally, I use the regular u substitution mainly, but there are times when I use the other version. Okay, let's do this. Here's another pair of the same problem. We can do it both ways. Traditional u substitution would say the inside function here will identify explicitly as u as 2x squared minus 3x, because that's inside this to the fourth function. The derivative of that would be 4x minus 3. So du would be 4x minus 3 dx. And that means that this is u to the fourth, and this 4x minus 3 dx is the du, which means this is u to the fifth over 5 plus c, which means that's 2x squared minus 3x to the fifth over 5 plus c. All right. That's the traditional way to do that. I would do it that way. Okay, now the other way to do it is to say, hey, this is the inside function here. What's the derivative of that? It's 4x minus 3. So I'm going to have a 4x minus 3 along with the dx as the inside derivative, the derivative of the inside. So I simply have to take the derivative of the outer function, antiderivative. And so that antiderivative is that same inside, but raised to the fifth divided by 5, and I add my plus c. So this is a really good example to show why you might want to use this, because if the whole inside derivative is already there, then you just have to undo the outside derivative. Okay, one more, a couple more. Let's do another one. Here's a traditional version. U substitution will explicitly show u is x squared plus 3x. Of course, you can be pausing this video to try this. Du dx is 2x plus 3. So du is equal to 2x plus 3 times dx. And then I can say this is the integral then of cosine of u. And now I've got a 6x plus 9. So what I could do is say, well, how can I get 6x plus 9 from this? To turn a 2x into a 6x, I can multiply by 3. If I multiply both sides by 3, then this would give me 6x plus 9 dx, and that means this whole thing gets replaced with 3 times du. So we have 3 cosine u du. The antiderivative of cosine is sine, and then we'll replace the u with x squared plus 3x again. Let's see. So this is the answer. Okay, to use that same idea, except the reverse chain rule, just recognizing the derivative of the inside. If this is the inside function, the derivative would be 2x plus 3. I have this as long as I divide out a 3. So if I divide this by 3 and multiply by 3 here, that makes this 2x plus 3, which means this whole thing gets absorbed in the du. So I have a constant 3, and I have the antiderivative of this outer function. The antiderivative of cosine is sine. Just copy the inside, tack on the c, and we're done. Okay, one last one. Again, try this on your own with the u and without the u. This is the one case where I usually would use this method over here on this right side. So if you do this the traditional way, you're going to identify u as 5x. The derivative is 5. Therefore, du is 5 dx. And therefore, dx is 1/5 du. So this can be rewritten as cosine of u. And the dx can be replaced with 1/5 du. The 1/5 gets put outside, and you have an antiderivative of cosine of u, which is sine of u plus our integration constant. and then you can replace the u with 5x again. So that's the formal way to do it. Now this is a case where I would use this when the derivative is just a constant. So I'm looking at this going, so the inside function is 5x. The derivative of that is 5, which means I need a 5 here. And I'm going to balance it by dividing by a 5 out here. Then I've just got 1/5. The antiderivative of cosine is sine of that 5x plus a c. This is the one case where I would use this definitely, in all times I would do that. If the derivative is constant, then you just divide by the constant. You can even think of it this way. Some people like to think of this problem like this. If you have a cosine of 5x, the antiderivative is cosine of sine, but because the inside had a constant times that answer, you just simply divide by the constant. That's another way to think of that problem. All right, so you're welcome to choose whichever method seems best to you. Most people stick with this, except when the derivative is constant, they use this other method. But you're welcome to use either one in either context, whichever seems best to you. Okay, so that's going to wrap up the first part video. We're going to do a second part to talk about how u substitution looks when you do definite integrals. So far, all of this has been with indefinite integrals.